We've investigated similar right triangles. Similar right triangles would mean all the angles are congruent. And we know that similarity in triangles involves the ratios of sides of triangles being proportional. So from the investigation we learned yesterday that if this is angle A, and this would be the leg opposite, this is defined as the leg adjacent, and this is defined as, of course, the hypotenuse. So trigonometry studies three ratios associated with angle A. The first ratio is the sine. The sine of angle A, which is just a number, is the ratio of its opposite over its hypotenuse. For any angle A, whether it be 32 degrees, the sine of a 32-degree angle in a right triangle will always be the same. The sine of a 32-degree angle will always be the ratio of the opposite side divided by its hypotenuse. The cosine of angle A in a right triangle, cos A, is always defined as the adjacent over the hypotenuse, and the tan of a certain angle A in a right triangle is defined as the opposite over the adjacent. Before we talk further, we're going to mostly just focus on tangent today, but I just want to put angle B up here. Of course, angle A will still be down here, but this is angle B. If I'm looking at this angle, which would be the hypotenuse of angle B? Well, the hypotenuse always remains in the same orientation. Which would be the side opposite angle B? Would it still be right here, which was what it looked like over here? Nope. The side opposite angle B, or the leg opposite angle B, would be here. The leg adjacent to angle B would be adjacent next to, would be over here. So notice that even though these two right triangles each have hypotenuse, opposite, and adjacent, it depends on the angle that you're looking at, and that's the orientation you want to focus on. Example 0, finding the following using the triangle on the right. If you have angle A here, what would be the sine? The sine is opposite over hypotenuse, 5 divided by 13. Cosine is adjacent over hypotenuse, 12 divided by 13. And tangent is opposite divided by adjacent, 5 divided by 12. I'm going to add something here. I'm going to talk about B. What would be the sine of B? Well, sine is the opposite over hypotenuse, so that would be actually 12 divided by 13. The cosine of B is adjacent over hypotenuse, 5 divided by 5 divided by 13, and the tan of B would be the opposite, which is 12 divided by 5. So notice how they do not look similar to the top ones. Exactly similar, but there is a relationship that you will learn in future years about the sine and the cosine of two different, these are complementary angles. You'll learn more about that later. Okay, maybe this would be a good time to introduce the notation or the acronym SOHCAHTOA: sine, opposite hypotenuse, cosine, adjacent hypotenuse, and tan, opposite over adjacent. So the phrase SOHCAHTOA, if I put it together, just refers to a way that you can remember the relationship. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tan is opposite over adjacent, the ratios. And again, these are just numbers. So we're just going to focus on tangents right now, which is in section 8.5 in your textbook. So an example, when the tan of A would be opposite over adjacent. Oops, we don't have this. But if it's a right triangle, we can use Pythagorean to find it by doing x squared plus 24 squared. Oops. equals 25 squared. If you do this out, you're going to get x squared equals 49, or x equals 7. So now that we have all the pieces, we can set up the ratio of the sides. The tan of A is opposite over adjacent, TOA. Tan is opposite over adjacent, so it would be 7 over 24. The tan of C would be opposite of C over its adjacent. It would be the opposite of what we just did, 24 divided by 7. The tan of angle B, well, what is angle B? Angle B is 90. So it turns out there is no opposite and adjacent leg for tan of B. So tan of 90 is troublesome, or we don't know how to deal with it because you don't have the opposite over adjacent leg. We'll talk more about that, and in future years there is actually no answer to this. Null set, no answer. Okay. Given that the ratio of tan A is 3 to 4, find the length of AB. Let's call this x. So if you know that the ratio of the opposite and the adjacent is 3 to 4, for this problem we're given the opposite is 9 and the adjacent is x. We cross multiply, or we can think of multiplying this times 3 and this times 3, so the answer would be x equals 12. For B, they want you to find the length of AC. Well, if this is 12, this is actually a 3, 4, 5 triangle. 9 squared plus 12 squared equals C squared. 81 plus 144 equals C squared. C squared equals 225. Square root of 225 is 15. Here's the answer here. 12 is the first answer. Tan of C. Okay, tan of C. So here's C, opposite over adjacent. It would be 12 over 9, which we can simplify to 4 over 3, which actually we can think about as 1.33. Note, tangent is all about the ratios of the sides. It doesn't give side values, only their fractional answer. So if I look at 1.33, that would tell me that the ratio of the opposite of C to the adjacent is in a ratio of 1.33 repeating to 1, or 4 to 3. Moving on to the next page is some practice using our special right triangles, the 30-degree one. So it wants you to find the tan of 30 degrees. Recall that, okay, BC, this is 1, which is the side opposite the 30 degrees. And so this would be like A, the side opposite the 30 degrees. What would be the hypotenuse, even though it's not, we just really want the opposite over the adjacent. But let's just review the 30, 60, 90. 1 is opposite the 30 degrees. The angle opposite the 90 is 2 times 1, which is 2. And the angle opposite the 60 degrees is root 3, or 1 times root 3. So the tan of 30 degrees is opposite, which is 1 over adjacent. We must rationalize the denominator, so we come up with root 3 over 3. That is the tan of 30 in a perfect answer, no rounding. What is the tan of 30 if CB equals 5? Okay, let's check it out. Well, if CB equals 5, we know the hypotenuse is twice 5. We know AB is 5 root 3 because of 30, 60, 90 length relationships. We have opposite over adjacent. Let's start this again. We have opposite of 30 over adjacent of 30. The 5's cancel. Now don't forget, you need to leave the one placeholder on the numerator. And again, we have root 3 over root 3. So of course we get the same answer. How about the tan of 60 degrees? Looking at this diagram, the tan is opposite, which is 5 root 3 over 5. Five root 3 divided by 5 is just root 3. Root 3 over 1, simply root 3. What is the tan of 45? Well, let's make a picture. And if you'd like to, you can assign numbers. Maybe, so this is 45 degrees. And you can give these two any numbers you want. So the side opposite, let's call it 2. What would be the side adjacent? It would be also 2. So the tan of 45 is always equal to 1. Since all 30, 60, 90s are similar, opposite and adjacent is always the same ratio no matter what the size of the triangle is or the length of the triangle. The ratios are always the same. We are going to learn how to use the table. It's on page 311 in your textbook. You might want to look at that before you come to class tomorrow, and we can talk about how to use the table. And we'll also talk about how to use the calculator to find tans. So to set up this one, you need to either use a calculator or a table. So let's write out the relationship. The tan of 10 degrees, is equal to x over 15. Now the tan of 10 degrees is actually a number, and it's also a button on your calculator as long as you have your calculator in degree mode. It's very important that your calculator is in degree mode and not in radian mode. If it's in degree mode, you can simply, if we were to get x by itself here, we'd multiply both sides by 15, and we'd get x equals 15 times tan of 10 degrees. If you plug that into your calculator just by multiplying 15 times tan of 10, you will get something close to 2.645. Notice I use the approximation here. Now, how would you solve y? Use Pythagorean to solve y, and let's check that tomorrow in class. For the next problem, we have 50 degrees. We need to find x and y. We have the side opposite. The 50 is 3. So I'm going to write this down. Tan of 50 equals 3 over x. Notice the x here is in the denominator. When you have the x in the denominator, it gets tricky to get it out into the numerator. It's not that many steps algebraically. But is there another tan relationship you can pick out that has x in the numerator, which means that x is now called the opposite? If I fill in here for 40 degrees, notice I would get tan of 40 equals x over 3. Now, if you solve this one correctly, you will get the same answer for this one as you will for this one. The answer for this one is approximately 2.52. So please take one of those methods, either this one or this one, to solve for tan, solve for x, figure out what y is, and we'll regroup on this in class tomorrow. Next class. Practice. Try these on your own. So again, we have two right triangles, so you probably have to find x first. And I forgot to put this in here. So you'll need this right angle here. So in other words, these are one of these all-purpose proportions. Once you solve x, you can set up a relationship that 4 is to x as x is to y. Of course, x is going to be a number. So see if you can do these two. These are challenging, but I think you can handle it. And good luck, and see you next class.